All right, so for this one, let's add together these two vectors. So we'll start off with a 20 unit long vector, 45 degrees away from the counterclockwise from the positive x-axis. And we'll go with this one here. Looks like it's going to be about, let's say, 7 units long. And we'll put it at 60 degrees counterclockwise from the negative y-axis. So before we even start here and get into the mathematics, let's see what our answer is going to look like. Let's add these two together graphically. So I'm going to first trace out my 20 units long vector. And it doesn't matter which order you go in. You could pick the first or the second vector to start with. Doesn't make any difference. So there's vector 1, the 20 unit long vector. And then I'm going to put at the tail of, at the head of that vector, the second vector. Looks like that's pretty well lined up there. Tracing that through. Let's try a different pen. There we go. So there's vector number 2. This was the 20 unit long vector. This was the 7 unit long vector. Now our answer, which I'll put in red here, our answer should look something like that. That would be 20 plus 7. And if we look at that, what that might look like on the page, we'd expect an answer kind of off like that. Kind of lightly sketching in there so it won't clutter things up too much, but somewhere in that neighborhood, that'd be our resultant. So we're going to expect a resultant that's mostly to the x direction, but that's definitely up. That little bit of down pressure, down force that the 7 unit vector is applying isn't going to be enough to counteract the results of that 20 pulling up at 45 degrees. So we're going to expect an answer off in that direction. So let's see if the math bears that out. So our first step in adding vectors together is to draw the coordinate system, which we've already done there. I'm going to label these. I'm going to call this one vector 1 and that one vector 2. And then we'll go ahead and break each vector up into components so that we can add these together. So for vector 1, we're going to have an x component and a y component. For vector 2, we're going to have an x and a y. We use sine and cosine to get our vectors, our components in the x and the y direction. So let's start with vector 1. Vector 1 is going to have an x component to the right. So it's going to end up something like that. That'll be our x. And then we're going to have a y component like that. So a y and x for vector 1. Vector 2 is going to have an x component that looks something like this and a y component like that. So those are what our components will look like graphically. Mathematically, we can use sine and cosine for that. Now, for vector 1, our angle is 45 degrees. If we pick that 45-degree angle to work with, then y is our opposite side and x is our adjacent side. So x would go with cosine, the adjacent side going with cosine, and y would go with sine, opposite side going with sine. So x is going to be 20 cosine 45. So if I go to my calculator and key that in directly, got 20 cosine 45. That's 14.142. My y component, that's the opposite side, so it goes with sine 20 sine of 45. And that also gives us 14.142 because angle of 45 degrees, you get an even split between the horizontal and the vertical component. X and Y are the same. Now, if we look at vector 2, we can see that I drew my components not quite the right way. I drew them so they were kind of aligned here with the x-axis, but that's not the angle I have. And that's okay. You can redraw them. You can go y first, then x. This is essentially just showing you how order doesn't matter. You can go x, then y, and you get to that point. You go y, then x. But if you draw the components so they include the angle, then you don't need to do any translation. You don't have to figure out, well, what is this other angle? Certainly with 60 degrees, it's not so hard, but if that was some weird decimal angle, then you'd have some extra work to do. So it's just easier to go with y and x this way. Here now we can clearly see x is my opposite side and y is my adjacent side. So x is opposite, so it goes with sine. So it'll be 7 sine of 60. So that's 6.0622. And y is my adjacent side, so that will go with cosine. So it'll be 7 cosine 60. And that'll give me 3.5. By far, the biggest mistake I see people make at this stage is flipping up their x and y components. So make sure you're really clear on that. It's usually a case of people thinking x goes with sine, y goes with cosine, or x goes with cosine and y goes with sine, getting tied into that math class structure. Here you have to base it on the angle. Opposite goes with sine, adjacent goes with cosine. So there we've got our components. Our next step is to add them up. So we have to take our sum of components in the x and the y directions. So we'll take our sum in the x direction first. So there's that funny looking Greek letter sigma. Well, for vector 1, I've got 14.142. And that's to the right. So it goes into the sum positive. For vector 2, I've got 6.0622. That's also to the right. Vector 2 pulls to the right. So it has a positive x component. So we can add those up, 14.142 and 6.0622. We've got a total x component, or the x component of our resultant, is 20.204. So our resultant, the combination of these two vectors, pulls to the right with 20.204. Do our sum in the y direction. For vector 1, we've got 14.142, and that pulls up. So that's positive. Up is positive. We've got 3.5 from vector 2, but that's down. So that's negative. those two oppose each other. One vector pulls up, the other pulls down. So there's a fight going on there. That means subtraction. So 14.142, and we'll subtract off 3.5. And we get 10.642. So those are the components of our resultant vector. So let's see what that resultant looks like. If we go down to another set of axes, just for clarity, rather than try to draw it on top of the drawing we've got already, we've got an x component of 20.204. So that x component is going to go out, let's say something like that, 20.204. And then we've got a y component that's positive, so it's up 10.642, so about half the length of the x component, 10.642. Now, due to space here, I couldn't draw it to the same scale as I did over here. But here we can kind of see our x component would be out this way. Our y component would be up like that, about half of that length. So it gives us the right picture. There's our resultant magnitude and direction. We can get the magnitude from the Pythagorean theorem. This would be our opposite. If our angle's here, that'd be our opposite. This would be our adjacent. So our magnitude would be the square root of the opposite squared plus the adjacent squared. So square the legs, add them together, take the square roots. And that is if you follow at least the methods I'm using here, it's the only way we'll ever use the Pythagorean theorem in this class. So it's always going to be square the two numbers you've got, add them together, take the square root. Generic math class dealing with the Pythagorean theorem, that isn't always the case. But in the way we use it, that's the only way we'll ever use the Pythagorean theorem, is to find the hypotenuse when we've got the legs. So 10.642, we'll square that. 20.204, we'll square that. Add them together, take the square root, we get 22.835. So 22.835 is the resultant magnitude. We need the angle, and the angle comes from the inverse tangent of the opposite over the adjacent. So our opposite side is 10.642. Adjacent's 20.204. Divide those, take the inverse tangent, and we get 27.777. So 27.777 degrees. It's a lot of sevens. Now, if you mess up the order here, it doesn't really matter for the magnitude if you screw up opposite and adjacent, because addition doesn't care about order. You'll end up with the same answer. Division cares about order. So if you flip this up and you put adjacent over opposite, you'll get the complement angle. You won't get this angle here, you'll get this angle here. So be careful of that. Make sure if you're drawing a picture out, you've got opposite and adjacent correct, so you get the angle that you've drawn in your pictures. All the time I get answers back saying, showing this picture, but then saying, well, I've got what, 60, 63 degrees, something like that as the angle. That's the complement angle. That's not the angle you've drawn in your picture. So make sure those are consistent. And again, think about it. Look at your answer, look at your resultant, look at the picture you draw of what that resultant should look like. We'd expect a fairly shallow angle to horizontal here from the way we drew our picture. 27 degrees is a pretty shallow angle. 60 degrees would not be a shallow angle measured from the horizontal. So that's the answer there. 22.835 at 27.777 degrees. Any questions on that one? All right, well, let me give you a couple to try out for yourself. And I'll just draw these up kind of in the same way I drew the other two or the other problems. And I'll give you some time to work on those. I'll pause the video so we're not recording dead air, or if any questions come up, we can ask those essentially privately. But I will record my solution of them so that you can go back to those later on if you need to review. So let's see, we'll start out with, let's say we'll do, so we'll add those two vectors together, 15 units at 50 degrees and 10 horizontal. And we'll do, let's see, I'll make that 4. We'll add those two together. All right, so those are our practicum problems. I will pause the video now. All right, so in the first problem here, we have a vector 10 units long pulling to the right, and then 15 units up and to the right at 50 degrees. To come up with an idea of what that looks like graphically, just as a sketch off to the side, we could put the 10 unit vector up that way, and this one's going to go, that 15 is going to be up and to the right. So we're going to expect something that is off to the upper right, but not quite as steep as that 15 unit vector is. It's going to be a little bit longer though. It's going to go out a little bit more to because it's these two vectors are working together a little bit. They're both pulling in the same direction in X, and at the very least, they're not opposing each other in Y. So let's go ahead and break these up. We'll call this one vector 1 and that one vector 2. For our X and Y components, let's do vector 2 first here for our X and Y components, because vector 2 is already all in the X component. It's all X. That means there's no Y. So when we do our sums, that'll be easy in the Y direction since there's no Y component from vector 2. Vector 1, that one we're going to have to figure out. Vector 1, we're going to have an X component looks something like that, Y component that looks something like that. So that'll be our opposite and our adjacent. Opposite goes with sine. So we do 50, we do 15 sine of 50. That'll give us 11.491. For the adjacent side, adjacent goes with cosine. So we'll do 15 cosine 50. There we get 9.6418. So there we've got our components. To add them up, we do our sums. So we have our sum in the X direction. We've got 11.491, and that's to the right. So it goes into the sum positive. From vector 1, vector 2, that's 10 to the right. So we get plus 10. And that'll give us 21.491. For the Y components, some in the y direction. From vector 1, we've got an upward pull of 9.6418. So that's upward, that's positive. We've got no y component for vector 2. So we don't have to put anything in for that. So there we go. There are the x and y components of our resultant vector. So our x component's twice as long as our vector 10 here. So that's going to go out to about there. And then we've got something that sits right about there for our y component. So drawing the resultant here in blue, I'm going to put something that looks sort of like that. To find out the magnitude and direction, we can draw it out down here a little bit more neatly. We've got an x component of 21.491. We've got a y component of 9.6418. And we want to know the magnitude and direction. Magnitude comes from the Pythagorean theorem. Square the legs, add them together, and take the square root. So 21.491 squared and 9.6418 squared. Add it together, take the square root. Looks like our magnitude is 23.555. And our direction, it's inverse tangent of opposite over adjacent. So we'll take 9.6418, divide that by 21.491, take the inverse tangent, and we get an angle of 24.163 degrees. And that meets with our expectations up here. We expected something pretty long as a result, since it was going to be a combination of these two vectors working together. But the angle was going to be relatively shallow, since most of the pull is in the x and we don't have a lot in the y. So 24.163 degree angle. Any questions on that one? All right, well, let's try the other one here. And I think for clarity, I'm going to go over to another page on that one and redraw it. So we've got our coordinate system, x and y. We've got a vector 4 at 70 degrees. And we've got this vector 6 at 30 degrees. Well, I'm going to call this one vector 1 and that one vector 2. If we graphically add those, well, we've got, let's go off to the side here, we've got vector 1 that looks something like that, and then vector 2 that looks something like that. So our answer looks like it's going to be to the left, but if my scale is right here, it looks like it's going to be up a little bit. So to the left and up is what I'd be expecting. So some vector off, kind of like that. Now it can be hard to tell depending on the angles and whether things are drawn in scale. This may be very close to horizontal, in which case it can be hard to tell if it's going to be above or below horizontal. So that's where we have to let the math tell us what directions things are in. And I'll show you in this problem how we know from the math what directions the components have to be in. So let's break these up here. Vector 1 will have an x and a y component. Vector 2 will have an x and a y. Vector 1, our x components over here like that, our y components up. X is my adjacent side, so adjacent goes with cosine. So I'll do 4 cosine 70. And there I get an X component of 1.3681. For the Y component, Y is opposite, so it goes with sine, 4 sine of 70. And that'll be 3.7588. So that's for vector 1. Vector 2, we're going to have an X component to the left and a Y component down. Well, X is adjacent, so that goes with cosine, so it'll be 6 cosine 30. That'll be 5.1962. Again, arbitrarily rounding to 5 sig figs here, since this is just a math problem. Y is my opposite side, so that will go with sine, so 6 sine of 30. And that gives me 3. So there are my components. If we do our sum in the x direction, we have from vector 1, 1.3681, and that's to the right, so it's positive. Vector 2, we've got 5.1962, but it's to the left, so that goes into the sum negative. So our sum, 1.3681 minus 5.1962, we end up with a negative 3.8281. Now we'll see how we'll use that negative here in a moment. Let's do our sum in the y direction. In the y direction, from vector 1, I've got a positive 3.7588. It's up, so it's positive. From vector 2, I've got negative 3, since it's pulling down. So my sum there is just 0.7588. So there are my components. Now, if we pause here and go back to the previous problem, we can see what we did with our components. We drew them out. I had a component of 21.491. That was positive, so I drew my arrow to the right. For my y component, I had a positive 9.6418, so I drew that up. When your components are positive, if it's an x component, you draw it to the right. If it's a y component, you draw it up. If they're negative, you draw in the opposite directions. So here my x component has a magnitude of 3.8281, but it's to the left. So if I draw x first, I'm going to draw to the left 3.8281. I'm still going to label it positive. The arrow is taking care of the sign. I've used up the sign by drawing the direction of the arrow. That's to the left, 3.8281. And then I've got to go up by 0.7588. So I'm going to zoom in on that here so it looks a little bigger than I've drawn it. There we go. So our components, we had an x component for our resultant to the left, 3.8281, and up, since our y component came out positive, 0.7588. Our answer, when we add the x and the y component together, is right there. That would be our magnitude and our direction. And with the picture, I don't have to worry about describing this angle as being clockwise from the negative y-axis. The picture describes it accurately. Now all I have to do is just say how much angle I've got here. I don't have to get into any weird referencing of angles from other axes. In math classes, we almost always reference our angles to the positive x-axis. In engineering, we almost never deal with an angle greater than 90 degrees. we try to keep all of our angles less than 90 degrees by referencing them to whatever axis happens to be most convenient. So you should never be keying into your calculator or getting as an answer from your calculator any angles bigger than 90 degrees. They should always be between 0 and 90. So let's get our magnitude. The magnitude here, we'll square the legs, add them together, take the square root, get our Pythagorean theorem going here, 0.7588 squared and 3.8281 squared. Take the square root, and we get 3.9026 as our magnitude. The angle is inverse tangent of opposite over adjacent. So 0.7588 divided by 3.8281, inverse tangent, pretty shallow angle. Our angle is 11.212 degrees. Now, common errors here are letting that negative sign creep in. That's usually the biggest source of error. If you take that answer for your x component and then you label it negative down here, if you do the Pythagorean theorem correctly, it shouldn't matter. But a lot of times people fail to include parentheses in their calculator if they have a line mode calculator, and that can mess things up. If you let the negative get into your inverse tangent, you'll get a weird angle. So you'll actually get an angle reference to the positive x-axis, and that could give you a strange answer. So I would encourage you to let the signs be held by the arrows. Always use positive values. Magnitudes are always positive. The size is taken care of by the length of the arrow. Where the arrowhead is pointing, that takes care of your sign. So when you draw these out, never label anything negative. It should always be labeled positive. Let the arrow direction tell you take care of the sign. All right, those are our two examples. Any questions there?